Yeah, welcome everyone. I think many of you don't know me. My name is Lita Lee. I'm a faculty member in the EAPS department, Earth, Atmospheric, and Planetary Sciences. One of the 3 faculty organizers for this semester's ICON seminar series. So as you can see, being a scientist, I'm kind of the rare ones among the ICON group. But today we have Professor Felix Herrmann here from Georgia Tech, and I think we are honored and actually very lucky to have Felix have escaped the hurricane.
That's right.
and arriving here. So Felix is also a geoscientist, but having many interdisciplinary research going on. He has appointments at Georgia Tech in the Department of Earth Science, Math, computing and ECE. So this is also a overlap that we both share. We talked about how we are probably the most applied scientists in our science department and probably the most sciencey colleague in the engineering department. So this intersection gives us a bit of unique challenges and maybe very interesting aspects to the problems that we solve. So I don't want to read the very long list of achievements that Felix has, but I want to mention 2 things. Felix went on a world tour back in 2019, supported by our Society of Exploration Geophysicists to give lectures as a distinguished lecturer around the world. And back in 2020, Felix was awarded the highest technological award from the society. So with that, the floor is yours, Felix.
Thank you. Thank you for the invitation, and it's great to talk to a broader audience. So yeah, as you said, my background is well, I did engineering physics back in the Netherlands way back, but now I'm at Georgia Tech, indeed at the Earth Sciences, Computational Science and Engineering and Electrical Engineering. So the talk will have a little bit of all. So I will be technical in the geosciences, but I may also sometimes be technical in the other areas. So hopefully everybody gets something from it. It's a technical field with quite a large amount of a number of challenges. And so what we're trying to do is so this is a technology that's really the only scalable and net negative CO2 emission technology. So you can take CO2 from smokestacks, or you can get it out of the atmosphere and then store it at very large quantities underground. And so what we try to do with digital twin is to help facilitate this technology, help it scale up, help the general public to get trust into this. So this is really very different from the traditional oil and gas, where you make money with everything. With CCS, everything costs money, right? So this work would not be possible without my students. I know my slides. Yeah, they're here. Some of them are still my students. Some just graduated. Some joined companies. Okay, a little bit motivation, right? So while we all doing our best to reduce the emissions of CO2, there's still quite a large amount of reductions that need to still be realized. And so that's tough. And as I mentioned in my introducing words, geological carbon storage, I prefer this wording over CCS or CCUS, is basically the only scalable and proven, even though a lot of people in the press tend to say it's not proven, but that's bogus, net negative emission technology. And it can really help us contain global warming by 2 degrees by the year 2100. To reach these goals, we have to store a massive amount of CO2. So we basically have to store 7 gigatons annually by 2050. That's a large amount if we want to basically meet these greenhouse reduction goals that are implied in the Paris Agreement. And so cumulatively, we need to store like 120 gigatons by 2050. if we do all that, it will take care between 15 to 20% of the CO2 problem. So that's not the silver bullet. It's not going to solve all of it, but it solves quite a lot. And it also really helps for difficult to reduce CO2 emission industries. So for instance, cement industry produces a massive amount of CO2, steel, and that's very difficult to get basically CO2 free. So it will basically take care of those industries. Right? So what basically means that we have to scale. So a lot of what we're trying to do is this digital twin is to facilitate the scale up of monitoring, that we are sure that we are doing the right thing. To give you a little bit of perspective, we need to have between 7,000 to 8,000 offshore injection projects, like the one that's been run in Norway for many years. That stores about 1 megaton per year. That's 10% of the CO2 produced by Norway traffic, right? So this is not small, but you need a lot of them. Now, there are hundreds of thousands of wells in the US, so this is not an unsurmountable amount, but it's not trivial. Okay, and so what people are really concerned about, the regulators and so on, is conformance and containment. Conformance means you lay out a plan how to store the CO2 on the ground, and you have to adhere to the plan. Containment means the stuff doesn't leak out. Okay, and so you want to be able to give assurances of safe operations. And what's very interesting, after you inject for 30 years and you wait for another 50, you have to transfer liability of the places where you injected CO2. So you want to know what's going on. Okay, so what is this CO2 or geological carbon storage? Right, so here you see a schematic. So this is offshore. I will talk mostly offshore because frankly on land there are complications that I rather avoid, and I can do that as a faculty member. And in Europe they're the furthest along of doing it on the North Sea. And so what do you have here? You have, of course, the sea, and then you have basically quite deep a reservoir rock, which is basically sandstone, which is porous and permeable, which can serve as a storage space for CO2. And there's an overburden that acts as a cap rock, which means that it seals the CO2 from going up. Now, you could argue, well, why would that work? Well, oil and gas has been stayed down under for millions of years. So these cap rocks typically will hold it down, but we would like to monitor what's going on. And so for that, we use, for instance, active source seismic to make images of the plume, and I will talk about it extensively, how we do that. On the right, you see a simulation, what's going on. So you see here in blue what we think the Earth may look like at an area that is representative for the North Sea. There's a seal on top, everything sort of in blue and green is a seal. And we simulated with a multi-phase flow simulation how this supercritical CO2, so the CO2 is injected as a supercritical fluid. Below 800 meters depth, CO2 turns into a supercritical fluid, means it's a very low viscosity fluid that can flow in the rock, and as it is injected, it will replace the brine that sits in the rock. So there's sitting salty water in the rock, and you push the salty water out in favor of CO2. Okay, so a little bit more about the scale up, right? So, I think there are different references, and there's a very good book by Ringo, if you're interested. But we need roughly like 12,000 of these injection sites to meet that goal of 7 gigaton by 2050. And then, so these are sort of the same information I showed before. There are lots of places on Earth where you can do that. You can do it in the Gulf of Mexico massively. You can do it in the North Sea, but there are other areas around the world where you have sedimentary rock that would be in a geological setting where you can do this. Now, this technology is not without risks, right? So you can have fractures that are induced because you pressurize the rock too much, or there could have been pre-existing fractures that you were not aware of. There could be a whole bunch of different failure mechanisms that make you want to come up with a system that tries to follow what goes on the ground, so we can mitigate certain risks. So if you talk about the risks, there are interesting sort of things going on. So it's dealing with the Earth's subsurface. We don't have direct access to the subsurface, so we don't know much when we start. But we will know more as we go, because as we go, we will inject CO2. We will come up with techniques that I will discuss that follows that plume using, for instance, active source seismic. So over time, some of the uncertainties with regard to the storage model will decrease. On the other hand, the containment risk increases because you inject more and more CO2 over time. And if that manages to escape, it will escape more later on because you injected more. Right? So there are these different types of risks that need to be mitigated. And on top of that, we need basically a continuous monitoring what's going on, because any lack of transparency in conformance, that is, that everything is going as planned, is absolutely necessary to not lose any confidence with the general public, right? So it needs to be all super transparent. Okay, so what's the challenge I will talk about today? This is a big topic. There can be hundreds of scientists are already working on this. And so you cannot solve this in one research group, but I will solve a number of problems that I think give us a pretty agile path from A to B when it is concerning the monitoring of this type of technology. So here you see what we will go into more detail. So you see again, here in the white box is the storage complex. That's the area that the regulator wants you to stay in, right? And that's sort of a legal framework that tells you how you should operate. So whenever you go out of this box, you violate containment. You see again here an injection well, you see a monitoring well, you see ocean bottom nodes that measure seismic, and you see very dense sources. Okay, and so this is what we think the Earth would look like. What we know, we don't know. So what we typically know is some probabilistic baseline, which I will talk about in a minute, that gives us probabilistic representation of the properties that rule fluid flow, and that's the permeability. So the permeability of a rock is the ease with which fluid can flow in the rock, right? You can have pore space in the rock, but if the pore space is not connected, you cannot flow. And so a measure for permeability is, measure for ease of flow is permeability, and it's a parameter that varies spatially. And here you see two realizations of this permeability from the baseline. They look quite similar, but if you simulate CO2 plume in it, it has a massively different footprint. So here you can see there's a high permeability streak that we were not aware of. You can see that after time step 1, you already sort of almost touching on the and almost go out of the box. So that's not what we want. So we want to develop a digital twin that is going to help us monitor it, but also make decisions. But we have to start somewhere. So I will do a lot of things. I'm not going to read this. It's a good definition of IBM. I will talk mostly today about what we call a digital shadow, which is a data simulation framework that allows us to guide the fluid flow simulations from measurements at wells and measurements from seismic. And so everything will be open source, and we do all of this to help accelerate innovations in this area and safeguard that everything works well. What's very important is that everything will be uncertainty aware. So this will all be cast in a framework of Bayesian inference, where we can say something about the uncertainty of the state that we're interested in. I will talk a little bit at the end about what we can do with control, but that is still that's going. So let's first start with establishing a baseline. So where do we start before you at all inject? And that serves as a starting point from how all the rest is going to work. And so for that, I'm going to introduce very briefly a technique that we've developed in seismic that's called full waveform inversion, which allows us to make an image of the subsurface physical properties from seismic measurements. And the way it works is it collects data with active source experiments. We will do these multiple times. So the baseline means before we do anything, and then there are monitoring surveys that we will do regularly, where we send in waves into the Earth, and they're being measured by either hydrophones or by ocean bottom nodes, and we collect data that looks like this. From this data, we can make an image of our subsurface physical properties, but we can also monitor the plume. Okay, so this involves a PDE, which we have to invert. So it's basically, for those of you a little bit more CSE based, it's a PDE constraint optimization problem where we try to fit the coefficients of the PDE such that they generate data that fits the observed data, right? And that can be solved with an adjoint state method, which involves solving the wave equation. So that's an expensive proposition. But with this, we can do that. But unfortunately, if you use that deterministic technique, you get typically only one Earth model, whereas there is, of course, uncertainty. So what we're going to try to do is recast this sort of, if you're a statistician, map type of estimate, maximum a posterior, where we really, in this case, only minimize the likelihood. You could add a prior term, then it would be a map. But we're going to do it to bring it to a more probabilistic setting. And we do that with a technique that's called variational inference, which is a scalable uncertainty quantification technique that allows you to go to very high dimensional problems. And we use an amortized technique because it will allow us to apply it after training to many data sets. And then a tool we will use extensively is a neural network that's called a normalizing flow. And so a normalizing flow is a neural network that breaks samples of a distribution that you try to learn. So suppose, I hate the example, but everybody can relate to it. I want to learn the distribution of cats. You give me 10,000 images of cats. I can give it to this network. And so the distribution of cats is very multimodal. But then I do a number of nonlinear operations that are learned. And the learning parameters here are the thetas, which are network weights. And the network weights are going to break the cat into white noise. So all the correlations that make a cat are going to be broken. And the statistical distribution is going to be Gaussian noise. Now, why do we do this? Because we use invertible networks. So we can invert. That means after we've done training, we can generate white noise and generate cats. Okay, now we're not interested in cats. We're interested in Earth models. So let me show you what that looks like. So here we have something that looks like an Earth model. So this would be the physical parameters in the Earth as a function of depth. That's the vertical coordinate and the horizontal coordinate. Of course, it should be 3D, but I showed for now 2D. And an epoch means the number of times I saw all the examples of Earth models that I trained on. And as you can see, as we pass multiple times through the data set, it manages to turn this Earth model more and more into white noise, right? So it breaks the long-range correlations, and it also shapes the non-Gaussian distribution into a Gaussian. Now that's nice because I can now generate Earth models that improve in quality as I'm better able to turn this into noise. Now, you can do other things. You can do diffusion models that are not invertible, but they invert with an iterative procedure involving the score. It's the same idea. Okay. So, so how are we going to use these? And so there's quite a lot of math going on. I try to keep the math a little bit light, but there is one slide that's important. And we use the technique that's called simulation-based inference. There's a beautiful paper by Kramner, Kyle, who is now in, I think, heads machine learning at Madison. He's a physicist, and they wrote a beautiful paper for the National Academy of Sciences, where they introduced simulation-based inference. And so what is simulation-based inference? So abstractly, you can think of it like this. Suppose I have access to samples of the prior. So again, I can sample cats. Okay. Now, conditioned on these cats, I can have another parameter, whatever it is. And now I can simulate data from X and from that, basically this nuisance parameter zeta, and that gives me Y's. And you can think of these, that is a sample of the likelihood, right? Given X, what's Y, right? But it can have a stochastic term. So there's no longer analytic expression for the likelihood. Everything is, what I do is likelihood free. I can just sample from the likelihood. Okay, and then the magic comes in of these normalizing flows, which can also learn conditional distribution. So here I give basically the objective of a normalizing flow, which is trying to minimize this two norm, where y is the data and x is the object I'm interested in. So say y is a distorted image of a cat, and x is a cat. In our case, that will be something else, but I'll tell you in a minute. After you're done training, that is, if you found the network weights, I can, conditioned on y, generate cats, which is basically I can generate samples from a posterior distribution that approximates the true posterior distribution. And the posterior distribution is the distribution of x given y, right? The likelihood is different, right? That's the probability of y given x. The posterior is the inverse. So that's an inverse problem that I have solved in this way. Now, unfortunately, the data sets are way too large. So I thought I had killed this slide, so I'm just going to skip it. I'm going to just show you images a little bit how this all works and how this gives us that probabilistic baseline. So here we have observed data. So we did a seismic survey before we did any CO2 injection. And from this seismic survey, I can try to get velocity models. So again, this is depth. So it goes to 3 kilometers deep, 6 kilometers wide. And in color code is the seismic wave speed that you see. And these are samples of the posterior. Unfortunately, it's very difficult to get these samples of the posterior from observed data. We have to do it from something else, which is, I'm not going to go in detail of, but if you're a geoscientist and you saw my talk this morning, I was able to do some sort of embedding if you're into statistics. And with the training on pairs, velocity models, embeddings, I'm able to train a network that can give us basically these posterior samples. So I do a survey, I map it to these CIGs, and from these CIGs, I can give you different velocity models, all consistent with the seismic data I collected. So this is a probabilistic representation of the velocities of the Earth subsurface, right? That I got from seismic methods that are sensitive to these properties because the seismic waves are dependent on the wave speed. And in color code, you see there the wave speed, and the wave speed changes as a function of position. So you get these gridded functions that represent different velocity models, all of which are consistent with the observed data that is sort of mapped to this embedding. Okay, now that's not the parameter we're interested in. So we're going to use now some empirical relationships that people have used to map these realizations of the posterior to these fluid flow properties, permeability that we're interested in, because those fluid flow properties are describing how the plume would grow if we inject CO2 underground. Okay, so there's some miracle here. I'm not going to go into math, but we map this. So here you see a 3D cube where you see different realizations of the posterior. You can see that they sort of, it's an unfolded cube. You can see that they vary wildly from realization to realization. And we translate these to even more wildly varying permeability distribution. So this is the permeability. Sorry, this should be a kappa, an old slide. But the kappa represents the permeability, which we fundamentally describe as a random field. Right? So we do not know what the fluid flow properties are. We say that we know the probability distribution of the fluid flow property. And so that's the baseline. So given this baseline and missing information of the most important property that would describe how CO2 plumes would grow underground, I'm going to try to come up with a system that deals with it by using data assimilation techniques. And so so that is basically a digital twin based on generative AI techniques. Okay, so the motivation then is that if you just do CO2 plume forecast, since we lack information on the permeability field, they're very uncertain. And so because we lack knowledge of the permeability, so we need to constrain these plumes by incorporating monitoring data. And so And that basically means that we're going to combine monitoring data with multi-flow flow, which will multi-phase flow, which describes the dynamics of how CO2 plumes develop, right? And so, okay, so what does it all look like? And I have a whole bunch of movies coming up, but I will go through some mathematics first. But this is sort of what goes on, right? So we have here in grayscale one permeability model, and then we would have a plume that develops because we inject CO2, so you see in grayscale a plume developing. That has an imprint on the image seismic. So what you see here are the observations from active source seismic. So if you have good eyes, you can see that there's a plume developing and it's growing over time. And we also have measurements at wells. So we drill wells, and at the wells we can measure the state of the plume, which is given by the saturation of CO2. So how much CO2 is there in the rock, and what's the pressure? Because you raise the pressure by introducing CO2 in the rock. So to come up with a framework that describes all this, we introduced basically a nonlinear Bayesian ensemble filtering technique. And so it's the emphasis on nonlinear, and I could also said non-Gaussian. So all the traditional common filtering techniques are out of the window because they make assumptions that don't hold. Okay, so the model is based on two equations. So one equation links the state. Again, that's the pressure and the saturation in the reservoir from the previous time step, so xk minus 1 to the next time step. And it's based on a realization of the permeability that's drawn every time I evaluate the dynamics randomly from that distribution for permeability models, right? And then the Q is injection rate, so how fast do I inject? And that's a parameter I can control. If I get to it and I have time, I will talk about that. Okay, so that gives you the time evolution or the transition equation that describes how the state evolves from k minus 1, where k is the time index, to the next time step. And then y is the observation. How do we remote observe these plumes? So this could be at wells or through seismic images. So that's an observation, right? And so we deal with these two equations. So to deal with them, we're going to state this all in terms of a probabilistic statement, where we cast it in terms of a Bayesian filtering problem, where we have probabilities that define the transition probability. So what's the probability of xk, the state at the next time step giving the previous time step? And we have also what's the likelihood of the observed data given the state, right? So these are two equations that go into a Bayesian filtering problem. And so we make some technical assumptions that it's a Markovian transition probability, so we can simplify some of these expressions. But everything is still likelihood free. We don't need to rely on explicit expressions for the likelihood. So if you are familiar with statistical inference for data assimilation problems, you always recognize 3 steps. So if you took a course in Kalman filtering, you should have seen that. If not, I hope I can at least convey some of it. So there are 3 steps. One is you start. So you start to initialize the state from some distribution, px0. Then you do a forecast step. The forecast step represents an integral over the previous time step and involves the transition density and the probability of the previous time step giving the data until the previous time step. Okay, this is a marginalization, if you're technical, where you integrate the previous step out, because the distribution here only depends, basically, only involve xk, not xk minus 1. Okay, so that gives you predictions for the state, but these predictions for the state are not necessarily correct. And so what you typically do in a Kalman filtering approach is you use an analysis step to correct the predictions so that they are consistent with observed data. And the observed data is the observed data yk. That's the data you collect at time step k, and you're going to try to basically, in the end, come up with a distribution where your state at time k is conditioned on all the observed data until time step k. Right, so this is the posterior distribution that you're after. And you can think of these two terms as a likelihood and as a prior. The problem with this is the modularization is impossible to compute. And so that's why people make assumptions. They say it's Gaussian, they do all sort of tricks that you can do it, but we're not going to do it. And so we're going to do is we're going to put this in terms of a machine learning framework. And I'm going to show you this by means of a bunch of movies. And so I'm going to go through these steps that a common filtering person would go through, but I will introduce machine learning techniques to do actually what we want to do. So what we see here are samples of the initial state. I have used some notation a little bit. So this hat means everything that has seen truly observed data. So that is something that comes from the field. Whereas everything without a hat is something we simulated in the computer. Hence this digital twin idea, right? Digital twin means you do something in the computer, but you also use data that you collect in the field to make correct the system. So you can see we inject with different injection rate, different colors, and at different locations. Okay, then we use the multi-phase flow to flow in different permeability models. Every time when we evaluate the dynamics, we draw a different permeability model, and that gives us these different realizations for the flow. So what you see here is the saturation field after one time step. And that's really, we sample predictions which are conditioned on the data conditioned initial state, right? So this is recursive, that's why I have this notation issue a little bit. Okay, so these are the states that are predicted, and from that we can simulate seismic observation. So here on the right, you see seismic simulations simulated in a computer, right? Nothing has done in the field yet, but this represents our understanding of the physics, how changes in the saturation result into changes in seismic images. Several pages of my paper deal only with that, but okay. So we have these two. So we have samples of the joint distribution xk, yk. And we can give those to a neural network to train on, right? And a neural network is going to come up with an approximation of the posterior with network weights that were estimated from this training ensemble. And so now we can have basically an approximation of the posterior distribution based on this ensemble. Now it's time to go to the field and collect data in the field, right? And so we collect now observed data. This is really data in the field. Now I simulated this data because we don't have data in the field yet that does this, but in principle, you should send your graded students into the field and collect the data, right? Or a company, whatever. And so that gives you this image. And now we're going to use this image to correct the predictions and turn them into basically estimates for the state that is conditioned on the observed data. So this entails a correction step where you're correcting on, conditioning on the observed data. And so that's the common correction step. The only difference is that we do this with neural networks rather than based on empirical covariances that you would do in traditional common filtering. I think I clicked one too many. It's a bit slow. Anyway, you do this recursively. So when you have these new plumes, they are the initial state for the next time step, and then you circle a line. So that's what we call the life cycle. Now, what is this correction doing? It's really at the heart of the digital twin, if I can get it. Yes. So you can see here this mapping of xk to xk hat. That's the mapping from this one to that one. That brings the digital representation into the physical world because you're conditioning this on y-ops. Y-ops are obtained from the field. So this is where the digital twin is informed by measurements that you take of the physical object. And that does the update to map these plumes to these. Okay, and so we do this using the properties of normalizing flows, where we do basically a mapping, where we use the samples that we trained on to go to the latent space, and then we take an inverse of the invertible network conditioned on the observation. So this is the nonlinear map that happens when you do data simulation, but with neural networks rather than based on covariances that you would estimate as part of a common thing. Okay, so there's some algorithms associated with this, which I will skip for the interest of time. So I have like 20 more minutes, is that right? Okay.
Felix, may I have
Yes,
a quick question?
sure.
So if you go back to your dynamics on the xk plus one, you had the m of xk.
Yes, yes.
Kappa. Kappa was the permeability parameter.
Yeah, and you draw that every time you evaluate the dynamics. It's a random variable. It's a random nuisance parameter of your statistic. And that really is the cause of systemic, basically epistemic uncertainty.
That's embedded in your simulation,
Yes. Every time I do a simulation, I draw a new field.
and you have a distribution of the kappa that's produced.
Yes, and that was derived from that baseline.
And then the m function.
It's a very complicated reservoir simulator topic by itself. People, whole science meetings are devoted to that topic alone.
So, but all of that gets you close enough that the correction is.
Well, that simulation is not close, but the seismic gets you close. Okay, and it does it through this latent space correction, but I'm running a little bit out of time because I have quite a number of slides still to go. Okay, so let's look at the case study. I have a ton of movies. Hopefully you can you can see what goes on. So this is a realistic project where we inject for 5.2 years about 1-2 megatons of CO2 per year. Okay, so let's look a little bit what's going on. So we simulate a ground truth. In real life, we cannot do that. In real life, we have only measurements in the field. But for now, we can compare to a ground truth. This is a very complicated CO2 field. And that's because it's a very complicated reservoir. And you see 24 time steps of the fluid flow simulator that describes how the saturation evolves over time. Then every 6 time steps, we take seismic snapshot. So you see the seismic snapshots here on the right, and you see the imprint of this guy in the seismic. And so we're going to use that. So we're going to use that to control basically and try to get as close as possible to this ground truth without seeing it, but only seeing it through the observed data seismically and also at wells. Okay. Just to show you how the permeability changes. So that's the property we don't know. This is how it changes. These are samples of the distribution of the permeability that basically controls the system, right? So the dynamics of the system are controlled by these fields, and they vary wildly. And that sort of encapsulates our lack of knowledge, what we think that's going on. Okay, and so we're going to try to compensate for this source of uncertainty by using monitoring data to steer our basically state away from the wrong ones. Okay, so here we go again. So here you see samples of the permeability. You see the initial state, and you see different plumes that are associated with this initial state and the different realizations for the permeability. So you see pretty wild variations among different plumes. That's because the permeability is crazy and the injection also changed. Okay. So now we generate training pairs for these guys. So here you see those plumes you just saw. We compute basically associated with it seismic data. So these are simulations in the computer. This is the pressure field. I didn't talk about that much, but you have the site from saturation. You also change the pressure in the rock. That is much smoother, but propagates out much faster. And that is a real risk when you do things on land, for instance. And here you see measurements of the pressure, and you have also measurements of the saturation at 2 wells. Okay. Okay, so here we have the ground truth again. And so this is what we try to get. And then on the right, you see inferences we get by sampling from the posterior distribution given every 6 times a seismic survey and averaging them. So that's the conditional mean. That's a very robust estimate for what we think the saturation is. Now, if you look at this carefully, you see that once in a while there's a jump. The jump occurs whenever I bring in every 6 snapshots seismic data. So seismic data is correcting the plume predictions whenever the seismic data comes in, and you will see whenever it jumps, it looks closer to the one on the left, which is the ground truth, which we normally don't have. And so that's what we can do. We can also look at the errors, and you will see that the errors also show jumps. So whenever new seismic data comes in, the error becomes much smaller when you correct with the seismic data, because the seismic data basically steers you in the right direction. The same with the uncertainty. So this is the variations among the posterior samples that tells you something about how certain you are about the saturation at that time step. And you can see also that in this case, we use both seismic and wells, that you see whenever data is injected from the wells, the uncertainty decreases near the wells, because that's where we have information. Now, what we're interested in, there is in our field for 50 years plus, an enormous fight between reservoir engineers, who are engineers, no, not scientists, they hate seismic. And they have people that do seismic and they don't like reservoir engineers. So reservoir engineers think we can do everything from wells, we don't need seismic. Seismic says we only need seismic, we don't need wells. What I try to show here, we need both, right? And so what you see here again is the ground truth. And you see here what happens when you use only wells. You can see that does not capture the complexity of the true plume, right? And that's because you don't have lateral information away from the wells. If you use seismic, it does much better. It captures this protruding high permeability streak that's responsible for this moving out, but it still makes errors. If you combine the two, it works the best. And that's, I think, really cool because it brings two fields together. And so you can see that at the last snapshot, you can see that basically in this case, you can see that this plume is the closest to that plume. And because you use a combination of seismic and well data. Now we can look at errors. Here again is a movie of errors. But let's look at the last time step. And you can see now something very interesting, which I didn't expect, but this is really something that should make the reservoir engineers happy, is because what you can see is that if you use seismic only, it's annoying that these things pop up. But at the bottom here, you see a lot of red. So sorry. And that is because there's still errors. Whereas if you inject wells, you will see that the error is gone here. And that means that the pressure at the wells still have a global effect. And the reason for that is because the dynamics is super nonlinear. Right? And so in this way, I think you can appease reservoir engineers and geoscientists, seismologists, that actually the two of them combined do a really good job. Okay, so that's for the error. We can also look at the uncertainty at one point. And you can see the uncertainty also behaves the best for both. And you can see, if you look carefully, that around the wells, whenever information comes in, you reduce the uncertainty, but not only at the wells, but also in areas everywhere. Okay. Now you can look at the more precise metrics. So this is following the errors. And so you see these jumps. So you do a correction, which basically, this is the correction. If you don't do anything, you just simulate. So then it's the error is horrible. If you use wells, you bring the error down a little bit. If you do seismic, you bring it down a lot. If you do seismic and wells, you bring it even further. But then after your correction, that makes you jump from here down here, you quickly lose basically information because you still use the wrong reservoir simulator because you have the wrong probability. But as soon as new data comes in, you do a new correction. You can see I do here 4 corrections. And so you control somehow the uncertainty that is due to the fact that you lack knowledge. Okay, so this is a digital shadow. I think people that do data assimilation would hate this term. I love it. And it basically means I only follow what goes on. I'm not doing any control. I'm not trying to manage, optimize, or anything. So I'm going to talk a little bit about that for the next 10 minutes, and then I should have questions. Okay, so first, control to injectivity. So you inject this CO2 at a particular rate, but that pressures the subsurface. If you pressure the subsurface too much, you break the rock, and then the CO2 blows out. So you want to very carefully inject. Okay, since we have samples of the state, which involves the saturation and the pressure, we can play games. And so we can play control games. So this is, there are control people here in the room. You could do something much more fancy, but it still sort of, it gives you the idea. Right, so on the top, you see here, basically the CO2 saturation from the digital twin at time step 3, and what it looks like at time step 4 when we predict it. And here you see the pressure. So there's both the saturation field and the pressure field. And whenever this looks red, it means I exceeded the pressure that can be sustained by the rock. It's the fracture pressure, which changes with depth. But a certain number of the realizations of the state of the plume violate this. And if I were to run this, I would lose sleep. So what can you do? You can try to reduce the injection rate from 0.05 metric, what is it, cubes per second. You can lower it, but you don't want to lower too much because that costs you money, because then you inject less. And so you can play that game. And the way we do that is doing a very basic statistical problem. We try to, for every state, we try to maximize the injectivity so that we stay away from the fracture pressure. That gives us a histogram of basically injection rates that are, how often they fracture, and we can then use that to control the injectivity, right? And so statistically what we can do is we can say, I want to make sure that at the next forest time step, I only exceed fracture pressure 1% of the time with a certain probability. And that's exactly what we can do. And we can do this if we lower the injection rate from 0.05 to 0.387. Right, so this is a control, right? This is something I can control operations, safeguard that I may be fracturing the rock, given the uncertainties that are present in the digital twin due to my lack of knowledge about what goes on in the system. Okay. Now, another one we can do is, if some people are familiar with experimental design, can I have budget, I can drill a well every year to do additional measurements of the plume. Where should I put them, right? That I maximally reduce the uncertainty. So here again, I use what is a digital twin, and a digital twin means there's two-way traffic, right? There's on the one hand, we have the twin, but we have also physical plume, and we can use the twin to basically drill new monitoring wells that help us control the system, right? And now a digital shadow becomes a digital twin because we are informed by the uncertainties of the twin where to interact with the physical system by drilling extra monitoring wells. Okay, so this slide for some reason takes a ton of time to get to the next. Yeah. Okay, so this is basically an instance of Bayesian experimental design where there's a beautiful connection between the KL diversions that we use to train these posterior distributions and the expected information gain. And so we can use all the mathematical tricks that we use to train the neural networks to keep track of the state of the plume. We can use these also to come up with ways to find locations of the monitoring wells that on average will maximally reduce uncertainty. Right? And so there's a lot of math there, but that's what we can do. And so if you look at it, you can basically optimize some mask that's parameterized by some a well density. And let me just show you in figures what happens, right? So suppose we are again at time step 1, we have these plumes, we have the seismic, and now from these simulations, we can come up with a density that tells me where should I put a well to maximally reduce the uncertainty. And so you can see, don't put one where the well is already, that's here in the middle, put one over here that will give us the best additional information to reduce uncertainty in the system. So we drill an extra well here next to the red one that we already had, and that's another one. So there's now an additional measurement at the well that we used in combination with the seismic, and that will reduce the uncertainties after I now condition on these two measurements that now also has information on the well. And that does much better compared to if you were to put the well locations random. So here you see it for 4 years. Every year I drill a new monitoring well. If I draw them random, there's still a lot of errors I make. Whereas if I do it with this expected information gain argument, you can see that the errors are reduced significantly. You can see here an imprint of these wells. So this is where it will put the wells to condition uncertainty on this film. So that makes it into a digital twin, because now we have basically, we brought the humans in the loop. We are controlling injectivity, we are controlling where we put wells, but you could do many more things. You can basically make decisions in the context of uncertainty. And I'm happy to see that there's some people in the audience that do decision-making in the context of uncertainty, and that's exactly what this is. So you can do things like Bayesian optimization or something like that. Okay, so that brings me to some of the, I'm not going to go over everything. I think I mentioned this. I think it's really important that we have engineers and geophysicists talk to each other. We need to do a lot of things. So one thing a critical person would say, well, if you get more and more data over time, can't you narrow the probability distribution somehow? Because you observe the field over many times. And actually we do that. And that's the last topic. And I have 1 or 2 slides on this. And we wrote, it's the most downloaded article in the Leading Edge, which is a leading glossy journal for geoscientists in exploration seismology, where we actually do this. So we have now an inversion problem where we take time-lapse data and we invert it directly for the permeability. And so we can do that in a probabilistic sense, and that would narrow the uncertainty in these permeabilities. So you can see really cool movies. So industry thought you could not do that. So let me just show a movie. You can see here, it builds up the permeability model. And with that, it basically, if you then generate a plume in it, the plume is very close to what the original plume was delineated with this white boundary. So that's an inversion procedure for the permeability. Yeah, that's it. Thank you.
Lots of time for questions.
Yeah.
Question about the injection rate. So, for your case, is the injection rate fixed with time or it's variable?
So for now, we looked at one time step. My student, but the student always goes off on a tangent, but in principle, the student should work to optimize this over multiple time steps. Very interesting control problem.
Okay.
Yeah. And so and you can do also the injectivity, you can do other things, right? You can stay away from the fracture pressure. You can also try to maximize the area that the plume, or the volume the plume visits, because that leads to more CO2 trapping, and that's something that people would like to accomplish. So you can solve beautiful optimization problems for that alone. But I think it's important that you inform it from the uncertainty of the plume, the state, right? You don't give it one state, you give it a family of states, and then you can make decisions in that context. Yeah.
It's nice to talk to you. I am worried about linking the permeability to the seismic.
Understood. Yeah, I know.
Yeah, that's the tough one.
Yeah, that's a tough one.
Porosity to permeability. Right?
Yeah.
And it's a whole nother story, but that permeability is probably gonna be a whole changing game during the whole.
You're totally right. So there are different models.
Yeah, I know, but if you look at, so you have an empirical model, right? And if you look at the scatter on that empirical model that you would fit in, right, probably seismic velocities to the permeability. You actually include the variance in those empirical models, which I think that's what you're using.
So, okay, so so not the last part where I invert for the permeability. And that's where we couple the two,
Yeah, yeah.
and that's where rock physics is.
Yeah.
But there's also rock physics in the data assimilation problem, because I have to go from the CO2 concentration.
Right.
So we use, and for now, we use just a patchy saturation model. However, this is the magic of machine learning. I can augment my training set with any rock physics model you want. Just throw it in there, make the training set bigger, and you will be able to generalize over that.
Yeah.
Now, if your rock physics in real life is completely different than any of these models you trained on, Houston, there's a problem. Then still you can use Bayesian selection techniques to see which of the models is active from the data. And you can also find out none of them is active, and then you may want to go back to the drawing board. You're totally right, but it doesn't change the framework. It would change the way you do the rock physics, right? So I'm with you. The problem is there are thousands of rabbit holes that you can go into, and I try to go from A to B, but this framework doesn't preclude you saying, hey, I have a much better rock physics model. Throw it in. Doesn't change nothing.
I don't know.
Well, yeah, no, but
They're equally the worst. They're equally the worst.
yeah, no, but you can throw many the worst in, and then
Yeah.
you will marginalize over it. So I didn't say the technical term, but what is happening here technically is you marginalize over the uncertainty of the permeability. That is no longer in your answer, but it is in the uncertainties. If you put in different rock physics models, you would marginalize over them, and it will be in uncertainty. So the uncertainty will get bigger. That's just what happens. Which is I can live with that. But you're very good point. Yes,
In your so-called common filter model, in the correction step, you're
Yes.
taking observation data every 6 time step.
correct.
Let's say if you increase the fidelity and do it every time step,
Yes.
do you foresee a optimization problem that maybe there's a time step where we draw observational data that makes the uncertainty the lowest?
So I think if you do that, but that's cost, you so this is the other cool thing you can do with digital twins. You can simulate in the computer what that would give you, right? There's an enormous cost associated with it, because if you shoot every year a seismic survey versus every 5 years, it's a huge difference, right?
Yeah.
But of course, that will allow you to steer the plume much better. Because what you saw now is you correct for it, but then it walks away because I didn't know the right permeability. And then when a new data set comes in, I corrected it. If you correct much more often, it's much better, but a surprise to me. But what I didn't show is, of course, you can have access in the wells every moment. But then you will have different time steps, so then I have to think about other ways of constructing neural networks to deal with that. Can all be done. It's just an additional, this is just a framework and you can add all these complications. I think it's a really cool framework. So I'm sure in robotics and in other fields, common filters are very common. And the correction step that we do here is just neural informed. And neural networks can deal with highly nonlinear, non-Gaussian. And so you just use your ensemble that you create in ensemble filtering as a training set for a neural network. Boom, that's it. Yes, sorry, I didn't see you.
Yeah, so when you say nonlinear Bayesian ensemble filtering,
Yeah,
is it basically like ensemble common filter, or is it more advanced?
I think you can call this, so Joseph Marzouk is I think #1 in the world on uncertainty quantification and data assimilation at MIT. He independently came up with a method like this. We found out later, but we do much more sort of evolved simulations. So I think you can call this an ensemble common filter, except that you don't learn basically empirical covariances, which would relate to second order statistics to do the correction steps that you do in an ensemble filter. You train neural networks to do it. Right? And so even though the ensemble common filter can work for nonlinear problems,
Right.
it gets into trouble if it's non-Gaussian. And also increasing the ensemble size doesn't reduce the error. Right, so there's a finite accuracy that you can get with these neural networks. I think you can, make the training sets bigger and bigger. You will get more and more accurate. But I leave that to a mathematician to prove. But there is really rigorous mathematics. But I think you're free to call this basically nonlinear ensemble common filter. Happy with that.
I had a question to follow up on that, but the covariance is very useful in a common filter, right? Because it gives you the uncertainty limits of where
Beautiful.
they could be.
Yeah.
In this setting, what's the equivalent uncertainty region, let's say, right, of your estimates?
What the region, you mean how variable are the plumes?
Exactly.
Well, they're pretty variable.
Yeah. But is there a quantification of it like in a common filter?
So, yes, because you have, so you could use the net, so for instance, what you could do is you could use the neural network to derive the covariances. Right? And so you can use all the quantities that people use for standard column. But you have all the other moments too, because these networks capture the full nonlinear, non-Gaussian statistics. But you could sample it because you have samples of the posterior.
I have a follow-up question on top of that. So, well, if I'm sort of trying to wrap my head around the uncertainty and the samples that you are getting.
Yeah.
From, either the inference or from the sampling step, right?
Yeah.
And the geostatistics, so there is point-wise statistics, but there is also spatial correlations between your physical quantities.
Sure.
Or even, a single quantity, velocity or
Sure.
probability.
Yeah.
And how are they considered, at which steps are they, the spatial correlations or spatial?
So this is the beauty of
comparisons?
these neural networks. So these normalizing flows. So everything is based on normalizing flows. But it's technically based on neural networks that can capture conditional distributions. That's all, right? So you can do this with diffusion models that do that. And so what normalizing flows do, they break the correlations, the long-range correlations into Gaussian noise. So they then also shape the distribution into a Gaussian. Diffusion models do that differently. They are denoisers, but they do the same, but they do it conditioned on the whatever you have observed, right? So in my case, that would be the seismic, or it would be the wells, or both.
Do you do that for the joint distributions of velocity and permeability, or do you do them separately?
So the only place where I use the permeability is in the dynamics. So if I have the state at the previous time step, I have an ensemble of them. So I have, say, 128 of them. I then apply 180 times, 128 times a transition to the next time step. All of these are using a different sample of the permeability. So then I go from xk minus 1 to xk. Those are the predictions. But the predictions are bad. So now I'm going to use a common correction step, or the analysis step, where I use these networks to condition it on observed data, and that corrects these samples. That's it.
Right. Well, let's thank Felix
Thank you.
again. We'll take a picture. I think we have a ceremony.
Okay, be careful.